Hello, this is Jason Kendall, and welcome to the next of my Introductory Cosmology lectures. I'm continuing the series based on Dr. Barbara Ryden's textbook, Introduction to Cosmology, and we're up to Chapter 3. If you're just tuning in for the first time, please go back to my Cosmology playlist and watch the series in order, starting from Chapter 1. Chapter 3 deals with some elementary concepts in space-time, and I'm going to contrast the Newtonian idea of space and time to the elementary ideas of Einsteinian relativity. But before we begin, I just want to give a big shout out to my Patreon supporters and my YouTube members. Their support means a lot and helps me to deliver more of this content to you. Both my Patreon and YouTube supporters always get first views of all my videos, as well as some other nifty little perks. So thanks to you for all who are supporting. Now, on to cosmology. There's a long history to the idea of the force and how we get to the idea of the gravitational force. Aristotle, in the lower left, from the 4th century BC, said that earthly objects followed straight lines, quote, to the center. This means that they're attracted to the Earth's center because of their natural motion. Yeah, the ancient Greeks did know that the Earth was a sphere. Aristotle also said that celestial objects follow curved lines that never end. This means that they're not attracted to the Earth's center, but rather stay fixed on the celestial spheres. There was no reason for this other than philosophical codification and a classification of the well-known phenomenon of the motion of the stars and planets. He did not posit any reason other than the celestial motions are perfect and that earthly motions are corrupt or impure, and thus they must be different. Impurities came from death and decay and sank into the ground. Celestial things were known to repeat for all known history and never sink into the earth. That's not science and doesn't give the reason for there being these two realms. Claudius Ptolemy, mapped the celestial motions and created a model by which people could predict the movements of the planets and stars. He was a 2nd century mathematician and philosopher, and his Earth-centered universe held sway until 1610. It was these measurements that were passed down through the centuries that made their impact. Nicholas Copernicus, who lived between 1473 and 1543, created a sun-centered model that ushered in a whole new line of thinking that, amazingly, arose from his studies of Greek antiquity, where Aristarchus had proposed a heliocentric model well after Aristotle's philosophy had been written out. It was the lack of naked-eye stellar parallax rather than some religious viewpoint that led geocentrism to be preferred by Plato, Aristotle, and Ptolemy. That this was picked up by the nascent Christians and incorporated into biblical scripture is where it became dangerous to assert heliocentric models. The influence was big on Copernicus. He, like Ptolemy, posited that the heavens were perfect, so all motions were in perfect circles, and his model included more of the same circle in circles than even Ptolemy's geocentric model did. But it was this idea of his, this heliocentric idea, which caused a lot of waves. He'd created the idea sometime in 1514, but didn't allow this book to be published until after his death in 1543. He, too, did not explain the celestial motions, but rather made a new model based on ancient Greek and Islamic writers, rather than really any new observations. Thus, it was more of a deep philosophical perspective change from the prevailing view that had taken hold from Aristotle's philosophy of long ago. Galileo Galilei picked up on Copernicus's ideas in 1610 with his first book, The Starry Messenger, which detailed his observations through his far-seeing look-glass or telescope. Galileo strongly advocated Copernicus's ideas, much to his detriment, but he advocated them based on his scientific observations of Venus, the Moon, the Sun, Jupiter's moons, and the stars of the Milky Way. His book, A Dialogue Concerning the Two World Orders, inflamed church leaders, especially the Pope, who was actually a friend of his. While Galileo was under house arrest, he did pen more physics books. Simultaneously to Galileo's travails, in 1609, Johannes Kepler published his Astronomia Nova, in which he elucidated his first two laws of planetary motion, that things move in ellipses and the equal areas equal times law. He also posited that some force, kind of like magnetism, must be acting on the planets from the sun to keep them in these motions. He later discovered and published his third law, the p²= a³ law. All of his work was based off of observations taken by Tycho Brahe. It was the combination of these new observations, the accuracy of the predictions, and the revival of ancient Greek heliocentrism by Copernicus and Galileo's audacious public outreach efforts that finally broke geocentrism's grip. This allowed for the rational study of the heavens and opened up all scientific progress on all fronts. In 1687, Sir Isaac Newton first published his Philosophiae Naturalis Principia Mathematica, or the Principia for short. In it, he detailed his laws of motion and formally defined the concept of a force. As a preliminary, all of his laws of motion apply to all matter. So then, what's matter? To answer that deep question, we start with the first law, the law of inertia. Let's say you have some object. It doesn't matter what it is. If it's at rest, it'll stay at rest. If it's moving in a straight line at a constant speed, it won't change direction or speed. Both of these statements will always be true unless the object is acted upon by some external force. Then it will start moving in some direction, or will change speed, or direction, or both. This idea of inertia is the obvious tendency of objects to resist changes to their motions. This idea originally came from Galileo, who used it as an argument in favor of Copernicus. Galileo thought about it in his windowless boat on a still glassy sea analogy. But Newton codified it into a coherent statement as a fundamental law of nature. Newton's second law is that a net external force applied to an object causes the object to accelerate at a rate that is proportional to the force and inversely proportional to its mass. This is the famous F equals ma law. If the net force is zero, then there is no acceleration, just as the first law states. So really, the first law is a special case of the second law. Inertia is defined in the first law is really more of a philosophical statement that tells us about mass. Mass is that thing or whatever that it is that gives matter inertia. Massless things, therefore, as per Newton, wouldn't experience inertia. However, if it's matter, it's got mass, and which can be understood by its inertia. And this is a really important idea. So back to the second law. This law then defines the notion of a force. A force is anything that causes a mass to accelerate, and mass is an intrinsic property of an object. It is the same independent of where it's located in the universe. Just to be clear, mass is not the same as volume or weight. Volume is the size of an object and its extent in space, but a kilogram of feathers takes up a lot more space than a kilogram of lead. And weight is actually the measure of the force experienced due to gravity or some accelerated motion. The force of you standing on a scale can be mimicked if you squeeze the scale between your hands, and this assumes that you're pretty strong. So the pound is not the same as the kilogram. Pounds are forces, kilograms are masses. Just to be clear, the international standard of mass is the kilogram, and a kilogram weighs about 2.2 pounds on Earth at sea level, but only about 0.3 pounds on the moon. But in both places, that bag of feathers or that block of lead is still just 1 kilogram. Now, Newton's third law is the one that really trips up a lot of people. For every force, there's always an equal and opposite force. For example, when you hit a ball with a bat, the bat hits the ball with exactly the same force as the ball hits the bat. So why doesn't the bat fly backwards into the bleachers as far as the ball goes away into the field? First, the bat is more massive, so its inertia demands that it resists motion more. Second, it's also attached to a person who helps add inertia to the hit object. Third, that person is bracing against the ground, which absorbs the hit too. The ball, on the other hand, is just itself, with nothing but air to help push back. So off it goes. Just to be really descriptive, Newton's third law states that when object X exerts a force on object Y asserts an equal and opposite force back on object X. Kind of confusing, but that's why I did the ball analogy. Looking at our diagram, we just see that F1 equals minus F2. So forces also have direction, opposite directions. Finally, we can implicitly define the concept of momentum from the first and second law. Momentum is the product of something's mass times its speed. A force applied through some delta t will cause a change in the momentum by, in the simplest case, changing the velocity, delta v. By the way, velocity is speed going in some direction, so there's always 2 bits to it, and all these add up to give us a really good picture of forces. They act on matter. Matter resists the change via inertia. Forces act through a time interval and must have some cause. And all objects can have their masses determined by applying some force to them and seeing how they accelerate. Thus, Newton defines for us the idea of inertial mass. This adjective applied to mass should scare you. It means that there might be some other kind of mass. But this all gives us Newton's ideas in a nutshell, and the giants whose shoulders he stood upon to get there. Let's continue thinking about things in a Newtonian way and compare the four known forces. First, let's look at the strong and weak nuclear forces. These bind protons to neutrons inside nuclei and mediate the nuclear reactions and radioactivity. Their ranges are extremely short and they are extremely powerful. By short range, we mean the idea of an atom size is about 10 to the minus 10th meters, and the size of a proton is about 10 to the minus 15th meters. As you can see, the weak force acts on a size scale that's 1,000 times smaller than a proton, and the strong force acts on sizes that are right about the same size as protons. Next, the electromagnetic force binds electrons into nuclei to form atoms. It also binds atoms to other atoms to form molecules, and they therefore mediates and determines chemical reactions. It, like the previous two, is extremely powerful compared to the gravitational force. The electromagnetic repulsion of two protons close to each other is 10 to the 36th times stronger than their gravitational attraction. The electromagnetic force is an inverse square law, where the force of attraction or repulsion drops off as the distance squared between the two charges. Now, we know that the protons in a nucleus of an atom are pushing against each other electromagnetically, but yet they're captured by the strong nuclear force. The attractive strong nuclear force, therefore, must be stronger than the electrostatic force to hold the protons together in the nucleus. The separation at which the electric repulsion becomes stronger than the nuclear attraction is about 4 proton diameters. At this distance, which we'll call the range of the nuclear force, and that's about 10 to the minus 15th meters, it can be determined by looking at the stability of atomic nuclei. Oddly, the strong nuclear force doesn't actually decrease with distance. What happens is that as you stretch the bond between two quarks, for instance, more and more energy needs to be invested until there's enough energy to create a new quark-antiquark pair, at which point the bond breaks and transforms the particles of the stretched out quark binding and make them into a new particle. When we therefore speak of the strong nuclear force, as applied between nucleons, i.e. protons and neutrons, we're really mostly talking about the exchange of two quark mesons in the form of pions. In contrast, the weak nuclear force is what's called a Yukawa-type force. This kind of force is characterized by a potential of the form of inverse r times the exponential of, say, minus kr, where k is some constant. So therefore, at a short range, where this kr, which is the part of the exponent of the e, is very small, the exponential term is just 1, and the potential becomes an inverse r potential, which then translates to an inverse square force law. Therefore, at very short subatomic ranges, the weak nuclear force is actually very similar to the electromagnetic force, and that's what got some people the Nobel Prize a while ago. But as soon as this exponential term becomes big, the force rapidly vanishes and becomes undetectable. In short, neither nuclear force behaves like a true inverse square law, but the gravitational force as conceptualized by Newton is an inverse square law. As envisioned by Newton, this force binds massive objects together on large scales and mediates orbital motions and tells cats which way is down so they can land on their feet. And since it's a force acting on masses, this means all of Newton's laws of motion apply. In contrast, Einstein's conceptualization of gravity is that there is no force. Moving masses simply follow the shape of spacetime. In practice, these two ideas about gravity only differ when there are very high speeds, where the maximal speed is encountered, the speed of light, and at extremely deep gravitational minima. But this latter phrase is how we talk about space and time in Newtonian language. But when we think of an Einsteinian, we say that it's a strong spacetime curvature. When speeds are slow and minima are shallow and spacetime is lightly curved, the mental frameworks of Newton and Einstein are indistinguishable. At this point, we need to do some important background on how classical and Newtonian space and time are conceived. The name for the shape of space and time in the Newtonian world is Euclidean. This, of course, comes from Euclid's 3rd century BC book, The Elements, in which he describes the postulates for all geometry. Euclid first wrote down and defined the concept of a straight line. The idea that only one straight line can be drawn through 2 points comes from him. That straight lines form triangles with straight sides arises from him. These notions are very familiar to everyone and underpin the thing we call common sense. Euclid's geometry was also highly idealized. This follows from the Greek concept of perfection and divine nature of numbers. As such, he wasn't really interested in measurements of straight lines on curved surfaces or lumpy surfaces. He was interested in the abstractly pure linear geometry with all the two-dimensional flat surfaces. He was also interested in how perfect triangles, squares, and pentagons made the Platonic solids, which we now see commonly as interesting dice for role-playing games. His notions of geometry were placed in a spatial, or more specifically, a topological construction of space itself. His postulates assumed an infinite space where you could set down straight lines going on to infinity, where they may or may not intersect, depending solely on their orientation. Also, as a mathematician, he imbued his writing with a sense of seeking out the truth of eternity. So, his studies separated the notions of space and time. In fact, his whole exploration was into the infinitudes of number and space. To him, they were the same. To that end, we call flat space Euclidean. By flatness, we'll mean that if you take a triangle of any size or arrangement and place it anywhere in the universe, it would look exactly the same in all ways. There is no positional or orientational variation in space that would alter or change any aspect of the triangle. This qualifies as a commonplace idea. It's the one you probably feel intuitively about space and that Newton would have been steeped in and knew very well. Let's now look at what might be a pedantic but very important quality of space. Nowadays, we think of spaces not just as filled with points, but also add an understanding of the distances between those points and the orientation of those positions in space. We choose an arbitrary origin in space in which we can measure any distance in any direction. This origin has nothing to do with the center of space. It's just that where we define our starting point for all measurements. As Dorothy said, there's no place like home. Next, we experience only 3 spatial dimensions, casually known as up, down, back, forth, and left, right. So if we wish to know the location of a point in space, we use vector notation. The 2 vectors u and v have 3 coordinates which show how many straight line steps we take in each given dimension to get to that point. The blue spatial grid helps show that. We call x left, right, y is back, forth, and z is up, down. The length of a distance from the origin in x, y, and z could have magnitudes of u1, u2, and u3, or v1, v2, and v3. In this diagram, we only show one vector from the origin, but we can have infinitely many such vectors. Here, the red arrow is the vector terminating at the destination point. The length of this arrow is the distance from the origin to the point that's the tip of the arrow or vector, and we'll call that length the Euclidean norm. It's pretty easy to see that this is just the extension of the Pythagorean theorem into 3 dimensions. That's what that bar bar u bar bar means. It's an extension of a squared plus b squared equals c squared for right triangles into 3 dimensions. The rectangular box in the grid shows us that this is just the distance from one corner of the box to the opposite corner. If you project the arrow onto any of the sides of the box, or rather look at the box on the straight at one side, you will see a right triangle. There will be 3 projected right triangles for the 3 symmetric sides of the box. Once we have the notion of distance from the origin to any point using the definition of the Euclidean norm, we can then use the definition of the inner product to get the distance between any 2 points, or if you will, the arrow tips of any 2 vectors. If you look carefully, you'll see that the distance between vector tips u and v is equal to the norm of u minus v, in parentheses, or together. But wait, if you see that big equation, v1, and set v1, v2, v3 to be 0, then you get the original definition of the norm. Therefore, the distance between 2 points can actually be thought of as moving the origin along the vector v and then determining the distance from that new origin to the point at the tip of vector u. All this is possible because we move in straight lines, and as we move in straight lines, we measure each part of the space in which we endlessly travel exactly the same way. There are no kinks, holes, or loops in Euclidean space. There's nothing to dodge or avoid or go around. Also, if you let this set of vectors sit for 1 billion years and come back, nothing would change. Euclidean space stays the same. Well, wait then, what about time? That's pretty easy here. Time is the same for all observers everywhere in Euclidean space. All clocks tick at the same rate, and all clocks everywhere are completely in sync with each other. Time is the same for everyone, no matter where they are or how they are moving, and time is not linked in any way to Euclidean space. They are completely separate philosophical entities, and the Greeks and Newton had no reason to think they were related in any way. In that way, we can visualize all space as kind of moving uniformly and regularly through time. And that's what the other diagram is showing. Pretend the universe is instead a two-dimensional flat sheet, and every second the grand universal clock ticks, and at each tick a snapshot is taken. This distance in time will be the same between each snapshot sheet across the entire infinite plane of the universe for every location in the universe. If nothing spatially moved in the universe, then the only travel would be forward in time 1 second tick at a time. This big sheet analogy is not going through another spatial dimension, it's moving through time. Thus, this grand cosmic clockwork is how Newton did conceive of time. This was his philosophical basis for the laws of motion, the calculus, and his mathematical conceptualization of gravity. As for Euclid, he sought the unchanging perfection of pure spatial geometry and mathematics, the constancy of the flow of time, and its complete dissociation from space was so inherent to him that he didn't even bother mentioning about it in his writings. Here we see the amazing definition of the force of gravitation. In Newton's idea, whatever the forces are that cause accelerations can be due to many things. You can throw something can explode and push things around, something can be pushed by flowing water, and something can be pushed or pulled by horses. Warm winds may even lift hot air balloons, and so on and so on. But gravity was new and different. Gravity, as Newton conceived it, is a force that is a universal property between any two masses and their relative distances. The force is defined and understood to be proportional to the product of the two objects' masses and inversely proportional to the square of the distance between them. What's even more interesting is that Newton did not posit that there would be any change in this force due to the object's composition or when the objects happened to exist. Mass and distance were the only things that went into the consideration. Now, for the initial understanding of gravity, we need to use the idea of a point mass. This means that the mass lives or can be considered to live, all concentrated at one point in space. Then the distance between any two point masses is easily understood using the Euclidean norm we just looked at. But if there are two planets, say, that are really big and are pretty close to each other relative to their sizes, such as the Earth and Moon, then we have to add up all the contributions from every little rock from the surface all the way down to the core for both the Earth and the Moon. The sum of all these little bits on each other's little bits and their requisite distances works out quite nicely to be represented by their centers of mass. We can regard all of a planet's mass to be at a point called the center of mass. It is that center from which we measure the distance, just like you see on the diagram to the right. We do know that planets orbit each other and that somehow the tides are related to this. I get into the tides and differential gravitational fields and rotating reference frames in a different video in my series, which I invite you to go take a stare at when you're done here. In the meantime, what matters is the primary interaction between their centers of mass for the classic equation you see here. And it is this equation that can be used to chart all the movements of all the planets about the Sun. It can chart the movements of comets and tell us nearly everything about the movements of stars around the Milky Way. And it's this equation that even led to the discovery of dark matter. It was also of some use in Newton's study of falling apples. By the way, the negative sign equation is meant to indicate that the force is attractive between the two masses. They fall towards each other, so the acceleration is such that the distance between them decreases. Now we look at one of the most important and frequently overlooked aspects about Newtonian gravity. There is no explicit time dependence for his force. It just is, and its effect is just present. Gravity's influence travels very fast, likely instantaneously. This means that if there are two planets separated by a big distance and one of them breaks apart into two big pieces and one piece moves away due to some force, this change is propagated to the other planet instantly. Or if two very massive planets are separated by a very big distance, so big they cannot see each other, and if the distance changes rapidly, then the force immediately changes, with the knowledge of that change happening at the exact same time. And there isn't any seen or perceived mechanism. This was a big unsolved problem since its origin in 1687. A fellow of the Royal Society, Richard Bentley, seen on the right, was interested in natural theology and developments in new physical sciences, and it was these subjects upon which he frequently corresponded with Newton. Importantly, in 1713, Bentley was in charge of the second edition of Newton's Philosophia Naturalis Principia Mathematica, or, as it's known in shorthand, the Principia. He often wrote to Newton about the cosmological implications of Newton's gravity, stating that the stars should all collapse into themselves under Newton's gravity, and Newton, of course, had no good answer. In fact, Newton was deeply uncomfortable with the notion of action at a distance. In 1692, in a letter to Richard Bentley, he wrote, "That one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one another, is to me so great an absurdity that I believe no man who has in philosophic matters a competent faculty of thinking could ever fall into it." Wow. For his laws of motion, he used this phenomenon of motion to explain the origin of various forces acting on other bodies. But in the case of gravity, he was unable to experimentally identify the motion or object or thing that produces the force of gravity. In 1713, in the second edition of the Principia, Newton wrote, "I have not been able to discover the cause of these properties of gravity from phenomena, and I feign no hypotheses. It is enough that gravity does really exist and acts according to the laws that I have explained, and that abundantly serves to account for all the motions of celestial bodies." Wow. Newton punted on the idea of how gravity worked, because he couldn't discern any understandable mechanism. He was also greatly struck that the motions of the planets as well as the terrestrial objects could be explained and modeled by his laws of motion and his laws of gravity. This is a great philosophical conundrum, and it stayed with science for an extraordinarily long time. There are, in fact, only a few things in science that we call laws. We call ideas that are matched by a preponderance of evidence theories. These theories are very good explanations of currently known data and often apply to just limited regions of measurements or conditions. However, laws, such as Newton's laws of motion and his law of gravity, are so well studied, understood, accepted, and are used in such a broad category of phenomena that we have extraordinary confidence that they will never be superseded by any observation. That's what makes them laws. Theories, by comparison, are subject to being thrown out if new observations or experiments invalidate them. Strictly speaking, so are laws too, but the chance that they will be thrown out is practically, and for all intents and purposes, zero. Here, Newton expressed great confidence in his law of gravity, which has held up for nearly all known phenomena for more than 300 years, all with no explanation or even a guess at the underlying mechanism. In order to discern the motions of terrestrial and celestial bodies, Newton had one great underlying assumption baked into his laws of motion and into his law of gravity. It was that the mass of an object as measured by its inertial properties is exactly the same as the mass that creates the force of gravity. Here I've shown that by equating F equals ma with gmm over r squared, and labeling the mass under influence, here a brick with wheels, as both an m sub g for its gravitational mass and m sub I for its inertial mass. Strictly speaking, these two measures of mass describe two completely different phenomena, and there is no absolute need a priori for the measures of these masses to be the same in each instance, and to be ascribed to the same property. Gravitational mass could have been very similar to the electrostatic charge. Its force is given by F equals Q1 Q2 over the distance squared, where the force experienced by two charges is proportional to the product of their charges divided by their distance. If the electric charge is present on or embedded in some kind of object that has mass, then the force will cause that mass to accelerate. But the charges have no relationship at all to the masses of the objects they live on. They're both different properties of the same object with no interdependence between them. Now, if the gravitational mass were some kind of charge that is a property of stuff that is different than the mass that resists motion via inertia, then you should be able to measure their difference. Here in this diagram, m sub circle with a plus is m sub Earth, is the mass of the Earth, or the green ball, the wheeled brick, an excellent toy that is available to you from, say, Amazon.com, would have a gravitational mass of m sub g. The force due to gravity is just the product of their masses divided by the distance between their centers of mass, d squared. Now, if we use our hand to push on this wheeled brick, then it will resist the acceleration with an inertial mass of m sub I. Newton's great leap, or assumption, was that these two processes yielded exactly the same measurement for mass. And because Newton equated the inertial mass and the gravitational mass, we call this incredibly important assumption the equivalence principle. And we can test this in many ways, but an important test would be if two completely different materials with differing masses fell at different rates in the location without any air resistance. David Scott, Apollo 15 astronaut, made such a demonstration on the moon on August 2nd of 1971. Let's watch.
Jim, we copied both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. Joe, you have a good picture there. I've got
Beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
Superb.
So how well known and tested is the equivalence principle? To understand that, we want to measure the acceleration of masses in a known gravitational field that are very near to each other and see if they differ at all. The equivalence principle posits that the ratio of the gravitational mass to the inertial mass is exactly 1, but any differential acceleration in some experiment will indicate that the ratio is not exactly 1. Let's look at some recent tests of the equivalence principle. Both of the two example tests are from the University of Washington, were the torsion experiments that you see listed here. A classic type of torsion experiment was first devised by Laurent Utvush in the 1880s and early 1900s. This experiment was essentially two differing masses on either end of a beam, kind of like an imbalanced barbell. This barbell was suspended in the middle, well, not really in the middle, but off-center, by a very sheer but strong wire of known tensile properties. This is all set up to balance three forces: gravity pulling on each mass, the tension of the wire, and the centrifugal acceleration due to the Earth's rotation. Now, if the setup is truly balanced out, then the masses won't be going up and down, and in fact they'll be restricted from going up and down, and the twisting of the wire will exactly balance the centrifugal acceleration due to the rotation of the Earth at the latitude of the experiment, and therefore everything will be at rest. If, for any reason, the bar, after it's all set up to be at rest, starts to rotate, then that would be due to an imbalance in the acceleration field between the two masses appearing in the centrifugal component of the laboratory frame. This rotation would then indicate a violation of the equivalence principle. As you can see from the definition of the gravitational acceleration at the Earth's surface, it is completely independent of the mass of the object, and at sea level for an idealized spherical Earth, it is 9.80665 meters per second squared. So if you have two nearby masses in a near-identical gravitational field, then the difference in their accelerations must appear in the ratio of m sub g to m sub I. Eötvös, in his 1908 experiment, was able to measure this to 1 part in a billion using this idea, and that's really quite excellent. Modern torsion experiments like the ones listed in this, the two that are referenced here, to amplify these ideas, taking into account more and more accelerations in the Earth's gravitational field, and even taking into account variations due to the physical setup of the lab and surrounding environment. The best of these get to 1 part in 10 to the 13th or 10 to the 14th. Then came a space-based test with the microscope mission by CNES, the French Space Agency. Always with acronyms, right? Microsatellite with compensated drag for observing the principle of equivalence. Or, more properly, in French from my AI friend over at Narakit,
Le microsatellite à traînée compensée pour l'observation du principe d'équivalence.
Thanks, AI robot. My French accent would never be as good. This CNES mission was led by a team at the Sorbonne University in Paris, France, with a large team of colleagues and co-authors, and the results were announced in 2017. The microscope mission tested the equivalence principle to an accuracy of 10 to the 15th, 1 part in 10 to the 15th, using the universality of freefall. The satellite payload is composed of 2 pairs of quasi-cylindrical concentric test masses, each made of different materials that all acted as gravitational sensors. The masses were allowed to fall freely while surrounded by their protecting Earth-orbiting satellite, and the satellite had these little bitty electrical thrusters that adjusted the free-falling payload with respect to the satellite, and it's the measurement of these electrostatic forces applied to the masses that allowed visibility into finding a potential differential output for each mass, and they were able to confirm the quality of freefall for these masses to 1 part in 10 to the 15th. This is like knowing the distance between 2 places 100 miles apart to an accuracy of half the size of a molecule of water. For the particle physicists out there, this is really interesting. If there really exists some grand unified theory of everything, meaning quantum gravity, then there would have to be some violation of this equivalence principle. For most predictions of quantum gravity, they state that some equivalence principle violation should appear at the 10 to the minus 13th to 10 to the minus 18th level. For now, though, no such violation has been measured, and the space of allowed quantum gravity theories has greatly shrunk by this measurement in the middle of the range. Basically, at this time, mathematical theories of quantum gravity are way ahead of the experimental capabilities. And the upshot of this is that we shall treat for this video series, as does the entire physics community, that the inertial mass is the same as the gravitational mass, and that gravity, in its currently experimentally confirmed form, is not a charge, but some fundamental property of the thing we call mass. This all goes by way of saying that the equivalence principle is on very solid experimental ground and has yet to be toppled. Now we want to look at how a distribution of mass density throughout the universe creates a cosmic gravitational field. This concept will result in what we call the Poisson equation. Given a density distribution throughout the universe, can we add up all the contributions from all the point masses and create a gravitational field that will tell any kind of test mass how it should accelerate? And the answer is, of course, yes. First, we look at the gravitational acceleration in its vector form surrounding a point mass m. Here, r stands for the radial component of the acceleration, and there's no rotational component to gravity's acceleration. Point masses only pull radially towards the center, and that's what that r hat stands for. It stands for the direction of the radial vector. Anything placed a distance r from mass m will accelerate towards the mass, and that's where the minus sign comes from. And since we said radially, this radial location can be anywhere around the mass. Therefore, we can imagine a transparent sphere around the mass. This sphere encloses the mass entirely, and if we're really smart, we can make up a surface area integral that tests the gravitational acceleration on each little tiny patch of this sphere. That's what we got on the right-hand side integral. That's what that means. So g dot a means the inner product of the vector for the acceleration at a place on the sphere and the vector associated with up from that patch area on the sphere. Well, if we add up all these dot products in the sphere, then we get 4 pi times g times the enclosed mass m. The 4 pi arises naturally because I chose to enclose the mass in a sphere. We can imagine that all the dot products on the left add up to the surface area of the sphere, which is 4 pi r squared. So the two equations you see here are strongly related and tell the same story. The right-hand surface integral is quite familiar to students of electrostatics as Gauss's law. This is, in fact, exactly Gauss's law, but for mass. What we need to do now is extend Gauss's law for gravity into a continuous distribution of mass throughout all space. We need to turn that m, which is for one mass in one place in space, to the mass density as a function of location in all space. Our first step is to expand the idea of the point mass to a distribution of mass across space. So we first define the Greek letter rho as a function of distance from some origin. Remember that this origin is arbitrary. It just helps us with the starting point in space and doesn't mean that there's any center to space. Now this density, rho, describes the density for each point in the universe. We're immediately jumping from point masses to discrete tiny bundles in the vein of Newton's calculus in 3 dimensions. Now, to get a mass out of density, we need to multiply it by some volume. And that's what the d cubed r means. It's a little volume element that looks like a tiny chunk of a sphere centered on the origin. Multiply this volume by the density, and you get a tiny bit of mass throughout the universe. All right, so what's this r-artic mess? We want to find the acceleration due to gravity at the point ending from vector r, as we see on the left. The r minus r tick is the difference in two vectors from the origin. This is basically saying we need to ask what the acceleration due to the tiny bundle of mass at location r tick is at the point we care about, r. The top in parentheses is a vector from r tick to r, and the denominator is the Euclidean norm, or distance, of that vector cubed. The ratio of these two is the distance squared from the bundle of mass to our needed test point. The long S is the familiar integral sum, asking us to add up all these contributions in the entire universe. One goal of all of this is to remove all the yucky vectors from our lives. Vectors drag around a lot of additional work that we might not really need. Luckily, there are things we can do that can hide the fact that we're doing vector calculus. First, let's do a vector dot product on both sides of the equation with the del operator, and this is what we call the divergence. The divergence is roughly a measure of a vector field's increase or decrease in the direction it points, but really it's a measure of the field's tendency to converge or diverge from a point. And that's kind of the point of the acceleration. It's radial, so we're going to expect it to be converging towards that point. To do the divergence, we just take the spatial derivative of the vector with respect to each of the spatial components of the vector. Here, because we luckily use spherical coordinates, we don't have any rotational components to the vector field. It's only a radial function. So we only basically need to take the derivative with respect to r and not r tick. Why? Because we want to use the divergence around our test point to measure how fast the acceleration field is changing as you step towards or away from our test mass's location. And since only the ratio on the right-hand side of the equation depends on r, this leads to the right-hand side derivative with respect to r of that nasty-looking thing in the big parentheses. Now we introduce an important mathematical hackety-hack, the Dirac delta function. It's a known and pretty scary theorem of vector calculus that the divergence of 1 over r squared is 0 everywhere except where r equals 0, and that's where it's infinite. So this is kind of weird, and to take care of it and its obvious non-physical nature, we have the funny Dirac delta function. And this function has two important features. First, the function is zero everywhere, except where its input is zero, and then it's infinite. Second, the integral over all space of the Dirac delta function is 1. This odd definition is both useful and works as a mathematical representation of point-like behavior. We use it for point masses, point electrical charges, and it has lots of other uses in physics and mathematics, but I diverge. So the divergence of that 1 over r squared is definitely 0 at every point except at the spot r minus r tick, where it blows up, i.e. it goes to infinity. But if we take the area integral of a sphere centered on that vector 1 over r squared, we would get 4 pi for any test spherical surface surrounding and centered on that center point. The divergence theorem from vector calculus that the volume integral of the divergence of 1 over r squared must be the same as the area integral of that same sphere of the 1 over r squared vector. A nicer way to think about it is to think that the gravitational field is like a flow inward towards the mass at the center of the spherical boundary surface skin. The amount of flow field going through the surface has to equal the sink capacity of the entire volume inside that surface. So that's really the essence of this divergence theorem. The result of this is that 4 pi times the three-dimensional Dirac delta function is the solution to the divergence of a 1 over r squared vector field, which is exactly what the gravitational field due to a point mass is. A really good place to read a lot more about this is David Griffith's textbook, Introduction to Electrodynamics. It has a couple of really great chapters and gives a full motivation and derivation of the Dirac delta function. So if this was confusing, I'd suggest looking that up. The next thing we're going to do is plug this result back in, and it makes a lot of things really easy. The Dirac delta function is 0 everywhere except where its argument is 0, and its total integral is 1. This means that if we look closely at this, the Dirac delta function will pick out the density at r. So you integrate it over r cubed tick, and it's going to pick out that value at r. Let's see what that looks like. And there it is. It's really simple. We see that the divergence of the gravitational field is proportional to the density of the matter at the point you're measuring. That should make sense. The divergence is a measure of the flow of the vector field towards or away from some point, and we know that's related to the density of material at that point and the mass that's contained near that point. That's exactly what we see here. Now we use the fact that gravitational acceleration is not rotational, so it doesn't have a curl, and that's what that del cross g equals 0 means. If this is true for any vector field, then we can easily define the source of the gravitational field. The gravitational acceleration is therefore definable to be the gradient of some scalar potential. Well, what's a scalar potential? Well, it's like a topological map. At every point in every location, there's a scalar number, height. The gradient points down the slope from higher numbers to lower numbers. Thus, each topological line is an equipotential, where the acceleration at a point depends on how near the next topological line is down the slope. Further, the arrow of down has to be at a right angle to the topological line oriented down the mountain. And all of these topological lines are identical heights. So at each point in space has some value for this potential. Elevation on a map is like this. There's no place where the elevation doesn't exist, and we only define the 0 point to be the sea level of Earth. But sea level itself is defined to be the radius of the Earth if the Earth were a perfectly smooth ball. And it spins, so really sea level does vary by latitude. And once again, go see my videos about rotating reference frames to learn more about that. But back to G. We call the potential phi, and it's negative to demonstrate that acceleration happens towards the mass that sources it and not away from it. Finally, the divergence of a gradient is the Laplacian of the potential. And this is the Poisson equation. This is the modern representation of Newton's law of gravity in a non-vector format. This equation shows that if we can determine the map of the gravitational potential, we can understand the density distribution. Likewise, if we know the density distribution, we can evaluate the potential. Typically, this formulation is shown because you can see that there are no vector quantities. This makes many gravitational problems a lot easier to solve. Both the density and the potential are scalar properties with no associated directionality. They're just values in space. The way to read this equation from left to right is the acceleration of a point mass due to the potential in space is a result of how matter is distributed in space, or matter density distributions tell all other masses how to move, or the shape of the gravitational map of the universe is determined by how matter is distributed in it. All right, now let's finish up by looking at the nature of the potential and the gravitational potential energy, which are different things. The gravitational potential can be described in two ways. One, on the left, is for a distributed mass, and on the right, for a point mass. Now, the integral on the left integrates all space to give the potential. And it seems kind of odd since we are stating that the potential is at one point. But the potential at that point does depend upon the matter distribution at all other points in space. And going back to the topological map idea for a moment, we have to reference against all other points on Earth, specifically sea level. Likewise, this integral abstracts all the gravitational fields at all points due to the density and the distance from them. On the right side, we see the far simpler concept of the potential as a function of a single point mass. Again, we want to use the scalar quantity of the potential because then we can ignore all the vector quantities for things like force and acceleration. And we can always get the force field by taking the gradient of the potential, and then we can get the force by multiplying the force field by the mass of the thing in that field. This potential is different than the potential energy. That's because energy is force times distance. So that's how that U of G shows that. One way to think about the potential is that it's the gravitational potential energy per unit mass. This is easily seen for a point mass m at the origin, which takes the form of U of G is equal to some mass times phi of r, where the little m harkens back to our brick on wheels. But that's just a long-winded way of saying that the gravitational potential, or just potential, is not the same as the gravitational potential energy, though they're simply related. Let's get back to the Poisson equation. It can be thought of as relating the gravitational slope of flat space that pulls on and is created by the matter density throughout space. Notice that this entire idea of the Poisson equation is built on the foundations of infinite space, a universal and separate clock, and a spatial topology that can be described as flat and Euclidean. And also, there's no mechanism for it. In the Einsteinian world of general relativity, all of these ideas can be and are violated and changed, and we get an explanation. This means we'll also need a fully relativistic version of the Poisson equation, and that'll be coming soon. That was a lot, but it sets us up nicely for our transition into the way of Einstein, that will motivate both special and general relativity. I'd like to thank my Patreon supporters and my YouTube subscribers, as well as all the great comments on the videos, and I hope you'll consider joining me as a subscriber or supporter. Thanks again, and we'll see you next time for Chapter 3, Section 2, The Special Way of Einstein.